This is Power 5's final presentation. Our project was to develop an off-grid electrical power system for lights, a security system, and a water pump and filtration system. Our group developed a system that will reliably handle this load of around 200 watts of constant power, and it will function under very little management, while still being cost-effective.
To achieve this, we've decided that we will be using Rich Solar's 200-watt, 24-volt solar panels. These are cheaper than most monocrystalline panels and are very efficient. We were able to get them very quickly, easily makes the required wattage, and is very cheap for that amount of watts. And it has an open circuit voltage that is for the battery, and it already worked with parts that we had. In comparison, another brand's solar panels and a lot of other competitors are slightly to much more expensive than Rich Solar's monocrystalline panels, have longer delivery times, with the same cell density, same weight, and same cell efficiency.
Both fuses and breakers are used to stop the flow of current in case of an overload, but they use different properties to do so. A fuse uses properties of heat from an overload to melt a small wire filament that is once melted that stops the flow of electricity. A breaker uses the properties of electromagnetism from overloads or short circuits to flip a switch and stop the flow of electricity. Both are very effective if the right size is put into a system. Upsides of each are that a fuse is most of the time faster in detecting an overload than a breaker, and initial costs of fuses are lower than that of breakers. Upsides of breakers are that it is resettable so that you don't have to replace it every time it overload like with a fuse, and it also can work as a kill switch. We chose to use a breaker in our prototype and main system because of the fact that it's resettable and can work in as an emergency kill switch if needed. In a traditional power system, in a structure, there is either a fuse or breaker panel where the main power enters the structure from the power grid and is distributed. The power enters from the power grid, goes through the transformer. After a transformer passes through the structure's meter, the meter is used to record how much power the structure is using, and after the meter, the power enters the fuse box or breaker panel and distributed to items that require power.
Moving on to our charge controller components, we have the MPPT charge controller by Rich Solar, and in order to choose our charge controllers, we weighed how many amps we need our system to output, and in our case, for our final design, we have a 40 amp, which will satisfy the needs for 3 different solar panels. And the reason why we're using an MPPT charge controller rather than a PWM is because they have a 99% tracking efficiency versus a 75 to 80%. 20% may not seem very significant over the course of 3 different panels and longer stretches of time. This will stack up. And now for our batteries, we have a lithium ion phosphate battery, which as of now is the best type of design for a lithium battery. Besides the pros of being able to withstand colder temperatures compared to lead acid batteries, lithium batteries also have a longer lifespan and is able to output more electricity without losing more of that said lifespan. So for our design, we decided to specifically use a 24-volt battery with 50 amp hours, and we decided to use the Expert Power brands. For inverters, there are 2 different types of inverters, pure sine wave and modified sine wave. And what each of these do, it means that modified sine wave is a more incremental inverter where over time the voltage is increased, but it takes longer to do so. Thus, you get a more staggered step as shown in this picture on the slide. While a pure sine wave, the increments are much faster and much more smooth, giving a more analog sine wave as shown in blue on the picture. And the reason why this is important is because the smoother the modulation speed, the longer devices that use this AC current from the inverter will last. Because of that, we'll be using a pure sine wave inverter.
For the wires, there's Wires are going from our solar panel all the way through to the inverter are larger to lower the loss of energy. Wires that are larger have a lower resistance, meaning there's less loss of power over a longer distance. The wires we used in our prototype, which will be used in our main system for this part, are 6 millimeter or roughly 10 gauge. The wires after the inverter may vary depending on what is being powered. The most common sizes used for lights and outlets are 12 or 14 gauge, and for larger appliances, 10, 8, or 6 gauge may be used depending on what the appliance needs.
Okay, so on to our prototype portion of the presentation. So here's the main diagram or sketch of our design. As you can see, we have the solar panel that sits on top, and it's a wooden base with a box in the center, which allows for our so-called power wall or power floor, if you will. And here are our support structures. So the base of the actual prototype itself is about 58 inches length and 27 inches width-wise. And so there's 2 levels of that. So there's a top level where the box or the power wall sits in, and then there's the bottom level. And on the right, you'll see the support beams. The actual box or rectangle that will support and hold up our solar panel is 58.7 inches long and 23.8 inches wide. And the box itself, which will encase our power wall, is 18 inches in width, 48 inches in length, and about 9 inches deep. Now, in that power wall, we have 3 main components. We have our rich solar charge controller, we have our LifePo 4 battery, 12 volt, 10 amp battery, and we have our inverter. And of course, we have the solar panel that will sit on top. In these model pictures, you'll see our final product on the right with our solar panel and the top on our power wall. And then if you actually open up the power wall, inside you'll see on your left the inverter, in the middle the small battery, and on the right you'll see the charge controller.
Overall, our prototype was able to successfully power the water team system and charge a laptop, proving our setup effective.
Okay, so moving on to our next steps. So, our main part is the solar tracking system. So, it would be ideal to incorporate a solar tracking module into the final barn system to ensure the maximum power generation year-round. To see just how effective a solar tracker would be, we attempted to create a system that would function on our prototype. So, to start off, we created a small-scale prototype of a solar tracking panel system. So a servo connected directly to the panel would move based on the direction of the sun, all coded with an Arduino microcontroller. The Arduino would gather information from 2 light sensors placed on either side of the panel mount. To get a better understanding of how it detects where the sun is, I'll show a diagram of the code. If one solar sensor is greater than the other, then the panel should move in the direction of the sensor. If the panel moves greater than or equal to 170 degrees, then move to 0, pointing towards the east. So when the panel is at 0 degrees, the panel is facing down vertically. And for daily tracking, now I think you can see that we'd want to move back to that 0 degree or maybe 30 degree mark to accommodate for the next day, to have the panel point east again. Now, for a yearly tracking system, the panel that was originally facing the sun the whole day has been tilted the other direction. And what that allows is for tuning in to the sun's position during the year. What we basically want to do is cut out the bottom code, which tells it to reset, because, one day the sun isn't going to be in a totally different position in the sky. It's going to happen, slowly over time. Let's go to the solar tracking prototype implementation. So once we got the code working and we had a functioning prototype, we started to look into how much torque we would need to actually spin the panel. And what we get is 0.49 Newton meters of torque. And that is how much it takes to accelerate and decelerate the panel with a motor. Of course, that's not including wind and other scenarios, but we'll get into that in a second. So, The reason we went with the motor here that we're showing on the screen, this is a stepper motor. And what a stepper motor does is it measures the motor's movements in increments, which means we can measure the position of where the motor axis currently is. So that allows us to measure exactly where the panel is sitting, and we're able to actually correct the panel and move the panel back to the position of where it was originally at. So this kind of prevents any interference, like outside interference with the panel, because we have the ability to read the position and set it to the last one that it was supposed to be at according to the sensor values of the light sensors. So moving on to sensors now. So what we went with was actually using mini solar panels. We went with 5 panels that cost $6.49. Of which we only need 2 panels to set on either side of the mount. By receiving a small amount of power, they're connected to an Arduino microcontroller that I've mentioned before, and the output of the light reading goes into an analog numeric reading that can be read by the Arduino. So for each panel, each reading will increase the more amount of light there is and will decrease the less there is. That's a simple power intake, and we've tested them with the Arduinos, and they are functional, so all is well. So moving on to the future design and research. So this is basically a basic design of what we hope would be implemented, a prototype that we created. So in this scenario, we have the motor which is facing outwards from the solar panel. We're looking at the solar panel from the side view, as we have in the previous photos as well. So we have a small gear connected to the motor shaft, and then a larger gear on top, because the larger the gear ratio, the less strain there is on the motor. So yeah, hopefully this will be implemented in some form in the future. That's the idea for our next steps. Anyways, we hope you enjoyed our presentation, and we hope it was clear for you to understand what's going on behind the scenes in this project. And yeah, that about wraps it up, so thank you.